Good morning, everybody. Today we will be taking up a small topic of mathematics, which is called as quadratic inequality. Now, this consists of two terms. The first one, which says quadratic, it means that there is a degree 2 polynomial for us. And the second term, which is inequality, it says that the expression is not absolutely an equality. Now, let us see what is this degree 2 polynomial. All of us know that an expression of this form ax square plus bx plus c, where a, b, and c are real numbers, a is not equal to 0. This is what is a quadratic expression. Why we are saying that this a should not be equal to 0 is that the term which is having the highest degree of x, that is 2, that should not become 0. If a was 0, then this particular term becomes 0, and we have just bx plus c, which will be called as a linear expression. As small examples of it, we can consider first one, x square minus 4, where if we compare with the standard expression, then a is 1, b the coefficient of x is 0, and c is minus 4. In fact, we can write this as 1 times x square plus 0 times x plus minus 4, and that will show to us that a is 1, b is 0, and c is minus 4. We may also have as an example minus 2x square plus 3x plus 4, where again by comparison a is minus 2, b is 3, and c is going to be 4 for us. So what we have seen above is what is a quadratic expression and typical examples of it. What we are going to consider now is a quadratic inequality. That is, we will be taking up a quadratic expression and comparing it with 0. Ax square plus bx plus c, when we compare it with 0 by a less than symbol, this is the first case of a quadratic inequality. The second type of quadratic inequality that we can have is ax square plus bx plus c less than or equal to 0. We read it as less than or equal to 0. The third type of quadratic expression, quadratic inequality, would be ax square plus bx plus c of the greater than 0 type, and the fourth, ax square plus bx plus c greater than or equal to 0. We'll be considering these four types of quadratic inequalities one by one, starting with the simplest one. So before we start with these things, we have to consider What is a quadratic equation? It is ax square plus bx plus c equal to 0 type. This type of equation, because its degree is 2, it will have two roots. Let us call them as alpha and beta. Then in that case, this ax square plus bx plus c, it can be written as a times x minus alpha into x minus beta. In fact, what we can notice from our elementary studies is alpha plus beta will be minus b by a, and alpha beta is c by a. So when we are given a case of a quadratic, the essential question before us is what are the roots? The roots alpha and beta, they are given by the formula x equal to minus b plus minus b square minus 4ac in the roots divided by 2 times a. If we take alpha with the minus connecting sign, then we may take beta with the positive connecting sign, and we will be getting the two roots. So if we have got a quadratic expression like this and we want to factorize it in this particular form, then it is essential that we know what the roots are. So the next step for us is how to factorize a quadratic expression. How to factorize a quadratic expression. There are several ways for factorizing a quadratic expression. For instance, the first one is by splitting the middle term, that is, if you are having ax square plus bx plus c, then this term we call it as the middle term and we try to write it as sum of two terms. And the way to do it is that when you split it as a sum of two terms, then you should be able to have that this alpha plus beta, which is minus b by a, and this alpha beta, which is c by a, both of them get satisfied. We illustrate this by means of an example. X square minus 3x plus 2 is the quadratic before us. We have to split this minus 3 in such a way as alpha plus beta so that this term becomes alpha beta. So what we do is we write this minus 3 as minus 1 plus minus 2, and we notice that if this we call it as our alpha and this we call it as our beta, then minus 3 has actually become alpha plus beta, and at the same time alpha beta has become equal to 2, that is this. So this is one of the ways of factorizing a polynomial, quadratic polynomial, or finding the roots alpha and beta. And what we find by this way of splitting is alpha is minus 1, beta is minus 2. In fact, if we try to see whether these are actually the roots, then if we are considering this equation, then the expression, because it is x minus 1 into x minus 2 equal to 0, x turns out to be 1 or x is equal to 2. So what we notice is that by means of the equations, roots are alpha is 1 and beta is 2. We now consider a second way of factorizing the quadratic. This second way is not by splitting of the middle term, it is by finding the roots of quadratic equation. What we have as a typical example is x square minus 3x plus 2. If we have to factorize it, then assume first of all that x square minus 3x plus 2 is actually 0. When we are assuming that it is equal to 0, the roots of the quadratic will be minus b plus minus root of b square minus 4ac upon 2 times of a, that becomes 3 plus or minus root of 9 minus 8 by 2, 3 plus or minus 1 divided by 2. So 3 plus 1 divided by 2 gives us 2, and 3 minus 1 divided by 2 gives us 1. So once we have found the roots, then what we say is that this particular quadratic, which had roots 1 and 2, we write it as x minus first root into x minus the second root. In fact, if we write it in this particular way, then we get this splitting in this particular way, which is exactly what we found out here also. So this is next way of factorizing a quadratic. As a third way to factorize, which we rarely use, it is by completing of squares. This method is often ignored, but this is quite powerful way of finding minimum, maximum, and several aspects. And so this has to be seen very closely. If we are given this quadratic ax square plus bx plus c, first step what we do is make coefficient of x square as 1. And if we are doing this, we have to take a outside, and inside the bracket we will be having x square plus b by a times x plus c by a. Once we have this much, we keep this a outside, and here we have to try to write these two things within a square. Try to get them in a square. So what we do is x plus half of coefficient of x, the whole square. This is what we attempt. And when we are attempting this, what is it that we are going to get? It is actually x plus half of b by a, the whole square. And what does this become? X square plus 2 times x into half of b by a plus b by 2a, the whole square, which is actually x square plus b by a times x plus b square by 4a square. So when we try to write in this particular way, x plus half of coefficient the whole square, then what we are getting is this particular expression. We notice that x square plus 4 times b by a times x square plus b by a times x, this thing has actually come here. That is, it has actually come here. But in the process, b square by 4a square has come extra. So we are actually removing that term minus b square by 4a square and retaining this last term c by a like this. So what we have achieved in the whole process is ax square plus bx plus c. It is a times x plus half of the coefficient of x, the whole square. And when we say half of the coefficient of x, what we mean is actually this particular term, coefficient of x, and not this particular term. We should not think that the coefficient of x is b. The coefficient of x has to be taken as b by a. So once we achieve this much, we have minus b square by 4a square plus this c by a. This gives us a times x plus half of coefficient of x, the whole square, minus b square minus 4ac by 4a square, the brackets close. This is one more method that we'll be using for factorizing the quadratic in case we are not able to accomplish it fast by the first method. Having seen these three methods of factorizing quadratic, we now go for the actual process of quadratic inequality solution. We consider the simplest possible quadratics and their corresponding inequalities. As a simple case, we have x square, the simplest possible quadratic. If we take up the inequality x square greater than or equal to 0 and try to solve it, then All of us know that the square of a real number is always greater than or equal to 0. This fact is known. So x can be any real number for this particular inequality. So what we find is that the solution for this particular quadratic inequality is R. As a next stage, if we are considering a quadratic of this particular form, x minus 1 the whole square, and we compare it with 0 and say that we have to solve it. Then again, for any x which is real, x minus 1 is also real, and square of any real is greater than or equal to 0. So we conclude that x minus 1 can be any real number to satisfy x minus 1 the whole square greater than or equal to 0. So x can be any real number, and we conclude that answer is all real numbers are allowed for this particular quadratic inequality. We now go for a slightly more general situation. We consider quadratics which are not perfect squares, but they are factorized forms. Let a be less than b. Then we are going to consider a quadratic which has been given in this particular form, a quadratic in factorized form. What we considered first was quadratics which were perfect squares. And now what we are considering is quadratics which are not perfect squares, but they are being given in a factorized form. So in this, the first possible situation that we'll be considering is x minus a into x minus b as less than 0. When we have this particular quadratic expression, what we notice is that this is one number and this is the second number, and their product is negative. If product of two real numbers is negative, then the conclusion is first number is less than 0 and second number is greater than 0, or else first number is greater than 0 and second number is less than 0. The connecting sign for us is OR. So what we see is x minus a should be less than 0 and x minus b should be greater than 0, or else x minus a should be greater than 0 and x minus b should be less than 0. The first one suggests that x should be less than a and at the same time x should be greater than b. And the second one says x should be greater than a and at the same time x should be less than b. We have to consider both the cases because of the term or. What this says is that if you are having two numbers on the number line, x less than a means region behind this a. The bubble here means that this point is not included. So x lies in this region and the other solution says that x should be ahead of b. X is greater than b. So if x has to be less than a, that is it has to be here, and x has to be greater than b here. This cannot happen simultaneously because there is no common region for this upper region as well as the lower region on the number line. The first one has a solution of this region, second one has a solution of this region. There is no common region, so there is no solution available for this case. So we say that the solution set is the empty set. If we consider the next case in a similar way, then we are plotting the two numbers a and b. The first solution says that x has to be greater than a, that is this region. And the second solution here says x should be less than b, this region. If both of them have to be satisfied simultaneously, what we notice is that this particular region is the common region for the arrow on the top as well as in the bottom. So what we conclude is that the solution here is the open interval a comma b. Once we have seen the solution for the first case as well as the second case, first one gives solution as empty set, then we have an or symbol, and the second one gives a solution of an open interval, that is this. So the final answer for us is a comma b, and we can write the solution is x belongs to a comma b, that is x lies in the interval starting from a and ending with b, excluding the endpoints a and b. It lies between the smaller number and the larger number. As typical examples, we may consider this case x minus 1 into x minus 2 less than 0. If we compare with the standard form, x minus smaller number into x minus larger number less than 0, then the solution for us by the above discussion is x belongs to a comma b. So the answer in this particular case comes out as x belongs to the open interval this. We may also write it as 1 less than x less than 2. Sometimes confusions can arise. Say if you are having this particular case, x plus 1 into x minus 2 less than 0. What we notice is that the format for the quadratic inequality was x minus a, x minus b. The connecting sign here and here between x and the other number were minus sign. Then the conclusion came out that the solution was this. So when we have this particular example, The connecting sign here is not minus, it is actually plus. So we have to write it as x minus minus 1 so that the connecting sign becomes minus. For the second bracket, it is x minus, the standard format is already there. So we write it in this particular way. So what we find is this is of the type x minus a number into x minus another number. It is less than 0, something similar to this type. Once we convert into the standard format, a is minus 1, b is 2. So the answer for us comes out to be x belongs to the open interval minus 1 to 2, that is a comma b, that kind of a situation. One may also write it like this as minus 1 less than x less than 2. So this was a case unlike the case of this one where the format was x minus 1 x minus 2, that is x minus something into x minus something, but here it was x plus something, so we converted it into x minus format so that it becomes the standard form. We may consider another example. X plus 1 into x plus 2 less than 0. Again, the standard format requires that we should have x minus, and in the second bracket also we should have x minus. So that forces us to write it as x minus minus 1, and the second bracket we have to write it as x minus minus 2. Once we have done this, what we have to see is the two numbers are minus 1 and minus 2. Smaller number out of them is minus 2 and the larger is minus 1. And what we have seen is that if we have a less than b and x minus a, x minus b is less than 0, then the answer is x belongs to the interval starting from the smaller number to the larger. So by this logic, we find that here the answer should be x belongs to the interval starting from the smaller number minus 2 to the larger number minus 1. Or we may write the solution also in this particular format: minus 2 less than x less than minus 1. Once we are through with the case of quadratic inequality of this particular type, we now go for the next particular type of quadratic inequality, which is x minus a, x minus b less than or equal to 0. When we read this, it is less than or equal to 0. So it has got two cases: x minus a into x minus b less than 0, or else x minus a into x minus b is equal to 0. The first one we have seen that x lies in the open interval a comma b, and the second one we know by quadratic equations that the solution is x equal to a or b. So when we combine both these solutions, what we get is x belongs to the closed interval a comma b, or else we can write it in this particular format: a less than or equal to x less than or equal to b. So the conclusion for us is x minus a into x minus b less than or equal to 0 will mean that x belongs to closed interval a to b, or to say x satisfies this inequality: a less than or equal to x less than or equal to b. We take up a small case: x minus 1 into x minus 3 less than or equal to 0. Then, by the above result that we have, x should be lying in the closed interval 1 to 3. That has to be the answer for us. If we take a slightly different example, x plus 1 into x minus 3 less than or equal to 0, then we have to convert into the standard form. What is the standard format? X minus a number, x minus another number. So we write this as x minus minus 1. The second bracket is already in the required format as x minus, so we do not trouble it. And once we are through with this, what we find is that a is minus 1 and b is 3. So the solution turns out to be x belongs to the closed interval minus 1 to 3, or we can write it also as minus 1 less than or equal to x less than or equal to 3. As a third example, we may also consider x plus 1, x plus 3 less than or equal to 0. So we convert it into the standard form x minus type of format. So both the brackets are now of the format x minus and an x minus. The numbers that are involved are minus 1 and minus 3, and this is the smaller number, and this is our larger number. So the solution actually turns out to be x belongs to closed interval a to b, that is x belongs to the closed interval minus 3 to minus 1. We may also write it as minus 3 less than or equal to x less than or equal to minus 1. Once we are through with this case also, then comes the case x minus a, x minus b greater than 0. We have considered the cases x minus a into x minus b less than or equal to 0, that is this. And we have also considered the case x minus a into x minus b less than 0. So now we are going to the third situation, that is x minus a into x minus b greater than 0. What we have is there is one number And the second number is this. The product is greater than 0. So what we can say is that this into x minus b is not less than or equal to 0. So less than or equal to 0, it gave us solution a to b. Therefore, not less than or equal to 0 will mean that x should not belong to this particular interval. So x should be less than a, or x should be greater than b. That is, x less than the smaller number a, or x greater than the larger of the two numbers a and b, that is b. We can also write it in this particular form as x belongs to minus infinity to a to represent this, union to represent or, and then the other solution set we can write it in this particular form. So what we conclude for this particular case is, in case the quadratic inequality is x minus a into x minus b is greater than 0, then this will mean x less than a or x greater than b. We can also write it as x belongs to minus infinity to a union b to infinity. We take up a small example for the purpose of illustrating this particular result. We consider this case x minus 1 into x minus 3 greater than 0. Then for us, if we are comparing with the format x minus a into x minus b greater than 0, then a is the smaller number 1, b is the smaller number 3. So the answer that we can have for this particular example is x is less than 1 or x is greater than 3. Or to put it in the form of intervals, it is minus infinity to 1 union 3 to infinity. This is the solution for the quadratic inequality x minus 1 into x minus 3 greater than 0. We now take up the fourth case of quadratic inequalities x minus a into x minus b greater than or equal to 0. We read it as greater than or equal to 0. So this is x minus a into x minus b greater than 0, or x minus a into x minus b equal to 0. This one says x belongs to minus infinity to a union b to infinity, and this one says x will have values a or else b. So combining both the solutions, if we are including a, then the bracket will become the closed bracket, and when we are including b, the bracket becomes another closed bracket, and so this becomes the solution. Or put in another words, x is less than or equal to a or else x is greater than or equal to b. So this is the fourth type of quadratic inequality. Now let us actually summarize all the four things. First one that we had was x minus a, x minus b less than 0. This meant that x belongs to a comma b, or to say a less than x less than b. When we took up the second one, we are moving under the assumption that a is less than b. When we took up the second one, x minus a into x minus b less than or equal to 0, then the conclusion was x belongs to closed interval ab, that is a less than or equal to x less than or equal to b. The third is x minus a into x minus b greater than 0. This meant that x belongs to, that is x is less than a or x is greater than b. And the fourth case, x minus a into x minus b greater than or equal to 0. It was x belongs to minus infinity to a, and here b to infinity, which we wrote it as let us now see the similarities and where the variations occur. If we had less than, then in that case we had less than strict inequality, and the brackets were open brackets. But if it was less than or equal to type of inequality, then the same thing less than or equal to less than or equal to came into picture, and the brackets became closed brackets here. That is, less than means we had open brackets, and less than means in the solution we had strictly less than. This case, less than or equal to gave us less than or equal to less than or equal to, and at the same time in the other form of the solution we had closed brackets. If again in the third case, if we had a strict inequality like this, then in that case we had a strict inequality in the solution, a strict inequality in the solution, and open brackets. And in case it was not a strict inequality, equality possibility was left open, like in the fourth case here, then less than or equal to, greater than or equal to, the equality option was kept open, and the solution, instead of having an open bracket, was having closed bracket. So if it is less than or greater than, the brackets will be strictly open. If it is less than or equal to or greater than or equal to, then the brackets will be closed at the points A and B. That is what we notice on a comparison of all the four things. Now, we go for some simple solutions, questions to understand these four results. We take up the questions here. The first question that we have is x square minus 3x plus 2 greater than 0. We are given a quadratic, but we are not given in the form x minus a, x minus b. So what we do is find a and b first. Treat the quadratic as equal to 0 and solve for x. What you see is minus b plus or minus root b square minus 4ac upon 2 times of a gives us the values as 3 plus minus root of 1 by 2, that is 2 and 1. So x square minus 3x plus 2, it will be actually x minus smaller number, x minus larger number. And as we have seen earlier, a and b will be the roots. We can write it in this particular form. So if you are solving the question x square minus 3x plus 2 greater than 0, then it amounts to saying x minus 1 into x minus 2 is greater than 0. And by the case this one strictly greater than, the conclusion will be this thing, x less than a or x greater than b. So what we find is x should be smaller than the smaller number, or x should be larger than the larger number 2. Or put in another words, x belongs to minus infinity to 1 open union 2 to infinity. So what we are observing here is that if you are given a question which is not in the factorized form as x minus a into x minus b, then you have to find it in the factorized form. So you treat this particular expression as an equation and find the roots 1 and 2. And what we find is that the given quadratic will be x minus the first root into x minus the second root. And once we have written the quadratic in the factorized form, we can then solve it by one of the four methods that we had discussed earlier. Once we are through with the first case, we take up another illustration, x square minus 3x minus 4 less than or equal to 0. We had seen the solutions in the factorized form case, but again, this is not given in the factorized form. So treat it as x square minus 3x minus 4 equal to 0, and x comes out as minus of b plus minus root of b square minus 4ac upon 2 times of a, that is 3 plus or minus 9 plus 16 by 2, 3 plus or minus 5 divided by 2, that gives us minus 1 and 4 as the roots. So once we are through with the roots, what we can do is we can write x square minus 3x minus 4 as equal to x minus the first root into x minus the second root. So this actually becomes x minus minus 1 into x minus 4. So x square minus 3x minus 4 less than or equal to 0. This means x minus minus 1 into x minus 4 is less than or equal to 0. And by the standard results that we obtained, x will be lying in the region between the smaller number minus 1 and the larger number 4. And we can also write it in this particular format: minus 1 less than or equal to x less than or equal to 4. Now, once we are through with these two cases, this is the answer for us. We now consider a third situation, which is a combination of the first and the second. We had illustrated the number line used for finding the solutions while deriving the four quadratic inequality solutions. We have here two inequalities. The first one was discussed a little before, and this was also discussed a little bit before. And what we found was this had the solution x less than 1 or x greater than 2. And this had the solution minus 1 less than or equal to x less than or equal to 4. One may check up the first one. It was actually x square minus 3x plus 2 greater than 0. And this was the solution. And the second one was x square minus 3x minus 4 less than or equal to 0. And this was the solution. Now, when both the inequalities are there, it means x should satisfy both conditions. So, how to find out which values of x are permissible? We take the number line once again, like this, and we plot the numbers: this 1, this 2, this minus 1, and this minus 4, this one and this 4. Now, this one suggests that x should be less than 1 or x should be greater than 2. This solution, we are actually marking it on the top portion of the number line. The second solution that is there before us, we mark it here 1 to 4. And as illustrated and explained before, this bubble means the point 1 is not included. This bubble 0 means 2 is not included. So we have to see here x satisfies both solutions means what is the common region for us. X lies here, x lies in this region. So what is the common region? If we examine this portion up till minus 1, then arrows are there in this region, but no support is available from this one. So this region is not to be kept. Consider this region between -1 and 1. There is a support of this line from the top, but in the bottom nothing is available here of this particular line. So this again is rejected. Consider the portion 1 to 2, that is this region. 1 to 2, this one is available, this portion is available, but nothing is available here. So again, rejected. No region is common to both. Now consider the region 2 to 4. 2 is not available here, but 2 is available here. 2 to 4, after 2, the region is available here, and region is available here also. So we can consider it. 4, this particular point, it is available on the top as well as it is available in the bottom. So we can consider the region 2 till 4, that is this. So what we can say is the acceptable region for us is ahead of 2 and till 4. So we can also write it as 2 less than x less than or equal to 4. We explain again. The first inequality that was there, that was having this as the solution. The second inequality that was there, that had this as solution. We want x should satisfy this as well as this. So we take the help of the number line and plot the points 1 and 2 and -1 and 4. The first solution, we are plotting it here on the top, and the second solution we are plotting in the bottom, that is 1 to 4 region. And after that we are trying to see what is the common region, that is x lies in both regions. We find that the region which is here was not acceptable because we had support from the top but no support from the bottom. This was not cooperating. Same way we had to reject -1 to 1 because this cooperated by giving a support, but this region was not available to support here. So rejected. Same thing applied for this region 1 to 2. And when we came to 2 to 4, 2 was available below, but 2 was not available on the top. So we rejected it. And remaining region ahead of 2 we accepted up till 4. And so we got the solution as 2 to 4. Open at 2 and closed at 4. What we see is that if we are given one quadratic inequality alone, then in that case we have solved it. If you are given one quadratic alone, then again this type of things we have solved it. Notice that one is greater than and the other is less than or equal to. The types are different. And in case we are given both types of inequalities simultaneously, then what we have to do is find the solutions of each one of them separately, mark them one above the number line, another below the number line, and then try to see what is the common region to both of them. And then answer will be x belongs to the common region, which you can also then put it in the form of inequality like this. Once we have finished with this, we now try to go for the next case, which is slightly different. We are given a quadratic inequality of the type x square minus 2x plus 3 less than 0. Again, this has not been given in factorized form. So what we do is we treat x square minus 2x plus 3 as equal to 0, then what we find is that the discriminant is 4 minus 12 minus 8 less than 0. So we don't get any real roots for this quadratic. So all the standard methods that we had above methods, they fail as we are not able to factorize it. So what we do is, in this type of situation, we notice that discriminant d is less than 0. But what is a? The coefficient of x square, that is 1, positive. In this type of thing, if we have a quadratic of this particular type, then the conclusion is no solution. Reason: if d is less than 0 and a is greater than 0, then ax square plus bx plus c will be greater than 0 for all values of x. And if d is less than 0 and a is less than 0, then in that case ax square plus bx plus c will be less than 0 for all x. In fact, this can be obtained by completion of squares method. We delve into it a little bit here for the reason that things have to be completed properly. So, what is the method for it? Ax square plus bx plus c. When we describe completion of squares method, we had done like this, and then we wrote it as a into x plus half of the coefficient of x, the whole square, minus b square minus 4ac by 4a square. This was done earlier. So this is a times x plus b by 2a the whole square minus d by 4a square. We find that this is greater than or equal to 0, and this block is perfectly positive because d is less than 0. So when d is negative, if a is positive, then this whole thing, which is actually this particular expression, it therefore turns out to be positive for all x. And in case our a is negative, that is this thing, then negative into positive, it turns out to be negative for all x. This is exactly what we have concluded in this particular portion, which comes by the completion of squares method. Once we have discussed this logic, we come back to the question. We had x square minus 2x plus 3 less than 0, and we had to solve it, and we could not factorize it because the discriminant for us was 4 minus 12 minus 8 less than 0. So what we see is that since the leading coefficient, that is the coefficient of x square, is 1, so a is positive and d is negative. So ax square plus bx plus c will be less than 0, greater than 0 for all x. That is what we found here. So what we conclude is x square minus 2x plus 3 has to be greater than 0 for all x which are reals. Therefore, x square minus 2x plus 3 less than 0, that is the given question, has no solution at all. The reason is that since the expression is always going to be greater than 0, the case when the expression is less than 0 will not have any solution. That is the conclusion. So answer is, for the given question, solution is the null set. We now go for another type of question. We call it as the fifth one. X square minus 2 times x square plus 5x plus 3. We are given that this is greater than 0. We are given that this particular thing is greater than 0. Minus 2x square plus 5x plus 3. Again, this is not given in factorized form. And what we notice is that the quadratic has a minus 2 negative, unlike the previous cases where it was positive. So, as the first step, we are treating the quadratic as an equation. What we get is x is minus of b plus minus under root b square minus 4ac upon 2 times of this, that is minus 5 plus minus root of 25, 4 into 2, 8, 8, 3, 24, 25 plus 24 divided by minus 4. That comes out as minus 5 plus minus 7, whole thing divided by minus 4. So minus 5 minus 7 minus 12, that gives us 3. And minus 5 plus 7, that is 2. 2 by minus 4 gives us this. So what we can say is that minus 2x square plus 5x plus 3. Take that minus 2 outside. We are taking minus 2 outside, so we are balancing with minus 2 inside. So this becomes minus 2 times. The quadratic inside the bracket will get factorized, not the entire quadratic straight away. It is x minus the first root into x minus the second root. So when the question is that we have to consider the quadratic greater than 0, it amounts to saying that minus 2 times x minus the smaller number into x minus the larger number, it is actually greater than 0. Since this quantity was less than 0, so product of two numbers is positive and one of them is negative will mean that the remaining bracket, the second bracket for us. So by the quadratic inequalities that we have considered so far, this is of the type x minus a, x minus b less than 0. X belongs to a comma b. So x will belong to minus half to 3. That is the conclusion that we have for this particular quadratic. We had minus 2x square plus 5x plus 3 greater than 0. We have considered the same thing out here. And so this particular thing is greater than 0. So the remaining thing here, this will be less than 0. So we are having the conclusion as x lies between the smaller number and the larger number. We take up one more situation out here. It is question number 6. Suppose the question before us was x square minus x plus 7 greater than 0. What we notice at the outset is that the discriminant, it is b square minus 4ac, that is 1 minus 28 less than 0. And what we notice is that a, which is the coefficient of x square, is 1. So when the discriminant is negative, a is positive and the discriminant is negative. We have seen ax square plus bx plus c will be greater than 0 for all x. Therefore, x square minus x plus 7 will be greater than 0 for all x belongs to reals. So the answer is the solution set is whole of reals. So we had a previous case where x square minus 2x plus 3 less than 0 had no solution. And we have this particular case x square minus x plus 7. It is actually greater than 0. Now, after reaching this stage, come for a small discussion. This was question number 6. So this should be 7 from question 5 and 7. 7, question 4 and 6, I should say. 6 was this particular thing, and 4 was this particular question. So what we can say from question 4 and question 6 is if d is less than 0, ax square plus bx plus c greater than 0 has solution R or empty set. There won't be a third possibility. Either it is the whole of the reals as it happened in question number 6, or else it will be empty set. Now, which one, that is the question. For that, put any value of x in ax square plus bx plus c. If expression is greater than 0, answer is reals. In case the expression is less than 0, answer is empty set. We try to illustrate this by using the same examples. X square minus 2x plus 3 less than 0. We found that d is negative. Therefore, by the above, x square minus 2x plus 3 less than 0 has solution all reals or else empty set. Which one? That is the question out of these two. Put x equal to 0 in x square minus 2x plus 3. We get the answer as 3, and 3 is not less than 0. So x equal to 0 does not satisfy. X square minus 2x plus 3 less than 0. So the answer is empty set as we saw earlier. But if you are taking up the case x square minus x plus 7 greater than 0. Again, d was negative for us. So put one value of x, say x equal to 0, in x square minus x plus 7. As earlier, answer is real or empty set. We get the value as 7. And 7, it satisfies the inequality. Therefore, answer will be not empty because x equal to 0 is satisfying. So the conclusion for us is answer is the whole of reals. We wind up the session by taking up one small question. It is question number 8. It is slightly different from the usual ones. 4x by x square plus 3 greater than or equal to 1. This does not appear as quadratic inequality. But what we notice is that this x square plus 3, it is always a positive quantity. So we can take this x square plus 3 to the other side of the inequality without affecting the inequality. Or to say, if you are multiplying both sides by x square plus 3, a positive number, then the inequality will not change. So the question becomes x square minus 4x plus 3 less than or equal to 0. As earlier, if we treat x square minus 4x plus 3 as equal to 0, then x becomes 4 plus minus root b square minus 4ac upon 2 times 1, that is 4 plus or minus root 4 by 2, that is 3 or 1. So what we find is this actually is expressible in the form x minus the first root into x minus the second root less than or equal to 0. So by the previous discussion, x will lie between the given numbers 1 and 3, or we can write the solution also as 1 less than or equal to x less than or equal to 3. So what was not appearing as a quadratic inequality, on slightly disturbing it, it becomes a quadratic inequality and we are able to solve it by the known methods. The last one for us today is another question which is slightly different but also comes within the realm of quadratic inequality. It is 5x minus 1 less than x plus 1 the whole square less than 7x minus 3. If we consider this, then there are two inequalities before us. It says 5x minus 1 should be less than x plus 1 the whole square as well as x plus 1 the whole square should be less than 7x minus 3. X must satisfy both of them. If you consider the first one, 5x minus 1 is less than x square plus 2x plus 1. That becomes x square minus 3x plus 2 greater than 0. And as we had considered in question number 1, it was x minus 1, x minus 2 product greater than 0. And the conclusion was x is in the region minus infinity to 1 union 2 to infinity. Or to put it in other words, x is less than 1 or x is greater than 2. Now what we have is the second inequality also has to be satisfied. So x square plus 2x plus 1 should be less than 7x minus 3. This gives us x square minus 5x plus 4 less than 0. If we treat it as an equation, x square minus 5x plus 4 equal to 0, then x becomes minus of b plus minus root b square minus 4ac upon 2 times a, that is 5, plus or minus root of 9 divided by 2. That gives us the values as 4 and 1. So what we find here is that x square minus 5x plus 4, it is actually x minus 1 into x minus 4 less than 0. So x should lie in the interval 1 to 4. So we had had a situation of two quadratic inequalities, but they were actually given in a blended form in this way. We separated them and then formed two quadratic inequalities. We solved both of them. And what we notice is that the connecting sign for us is and, that is, x must satisfy both. So we now come to the number line once again for assistance. The numbers which are crucial for us are 1 and 2 from here and 1 and 4 from here. The first one says that x should be less than 1, that is here, or x should be greater than 2. The second one says x should lie in the interval 1 to 4. The bubbles actually mean that the points are not there. This means x exclude 1. Now, if we see the two number line situations, this particular portion up till 1 that we have, this line supports it, but there's nothing from the lower region, nothing to support it, so we exclude it from the solution. We need that there should be lines from the top as well as from the bottom. If we consider this particular region, then there is a support of this line for that region 1 to 2, but there is no support here, so we again exclude this particular region. 2 to 4, when we consider, 2 is not available here, but 2 is available here, and 2 to 4 region has got support here as well as support from here. So what we do is we keep the region 2 to 4. 4, again we can notice it is having support from the top here, but it does not have support here. So we have to exclude it from the solution. And finally, when we consider this particular region, there is support from the top, that is line is there, but there is nothing here. So again, we have to exclude this region. So we conclude therefore that X should belong to the region 2 to 4. That should be the answer for this question. Time doesn't permit, so we wind up the session here. What we have done is we have discussed what is a quadratic, we have discussed a quadratic equation, we have discussed the simplest form of quadratic inequality, x square greater than 0, x minus 1 the whole square greater than or equal to 0 types. We have considered x minus a into x minus b less than 0, less than or equal to 0, greater than 0, and greater than or equal to 0. We have considered the methods for it for solving. We have considered the case of completion of squares and splitting of middle terms as well as finding of the roots for solving quadratic inequalities. We have considered extreme situations like x square minus x plus 7 greater than 0 as well as x square minus 2x plus 3 less than 0, where the solution is either the empty set or the reals. We found out why the situation will be like that as well as gave illustrations by test checking with one particular point. And so, in this process, we have discussed several things. We discussed the case of two quadratic inequalities also, simultaneously two quadratic inequalities if they are given, how to solve. We considered question number 8 where it did not appear to be a quadratic inequality, but we had to convert into quadratic inequality. And finally, question number 9 where we had two inequalities which actually was blended quadratic inequalities. Two of them, we separated them into two pieces and then solved each one of them and then found the intersection of the two solutions to wind up that x belongs to 2 to 4. So in this session we have done this much. Much more can be discussed where we will have the situation of ax square plus bx plus c with a as not equal to 1, negative, or rational or irrational. But time doesn't permit, so we wind up the session here. Thanks a lot.